Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson number 10 on additional triangle proof. So I wanted to throw in one last lesson in Unit number 3 where we looked at just a variety of different proofs, both t-table proofs and paragraph proofs, some of them a little bit longer, some of them not that long, but just to kind of reinforce all the ideas we've seen. Because so far it's been a day on SAS, a day on AAS, a day on hypotenuse leg, etc. So you kind of had a good sense of what was coming. Here, as we attack each proof, we may not know which of the triangle theorems that we should use, and we'll have to decide that within the sort of larger structure of the proof. So let's jump right into it with maybe the most challenging proof we've done so far. All right, exercise number 1. In the following diagram, it's known that ED is congruent to FD, EB is congruent to FC, and DA bisects EF. Prove that triangle BAD is congruent to triangle CAD. All right. Now, this is a much longer proof than what we've seen before, so we really want to make sure that before we jump in to the actual writing of the proof with a t-table, that we more or less scope out how we're going to do it, and that's really part A. Let's take a look. It says first, draw out a diagram to plan how the proof will work. And by a diagram, I really mean kind of like, this is going to go to this, is going to go to this, not so much a diagram like a picture. Work backwards by thinking about what you will need and what you know. Then sketch out a rough plan for how to attack the proof. Well, what I'm going to do right now is I'm going to switch over to red so that we can really understand which two triangles we're trying to prove congruent. So we want to prove that triangle BAD is congruent to triangle CAD, right? And it could even be helpful to draw those kind of separately somewhere on your paper or on a different sheet of paper, something. But keep in mind, I need to show that triangle is congruent to that one. Probably, well, not probably, but definitely with one of the now 5 triangle congruence theorems. Okay, let's start to mark up givens. I'm going to go back to blue in order to do that. All right, really important to know what we know and know what we don't know. We know that ED is congruent to FD. A little bit challenging to show that. And we know that EB is congruent to FC. All right, and we know that DA bisects EF. So that means that this, here maybe I'll mark it with 3 marks, is congruent to that. All right, so that is what we know so far. We also know when we're specifically thinking about the two triangles that we're trying to prove congruent, we do know, right, maybe go 4 marks there, that they share a side. So that's kind of nice, given that, all these triangle theorems have sides congruent to sides. They share a side, so that's sort of one piece of information that's already taken care of. Now, it's not enough, obviously, right? We need more here, okay? But if you think about it a little bit, let's talk about what we can do. Well, based on the fact that we know that this long side is congruent to this long side, and this shorter segment is congruent to this shorter segment, we can do a little bit of subtraction to eventually show that this side is congruent to this side. In other words, what is that? BD is congruent to CD. We'll be able to do that through subtraction. So I'm going to write that down. By subtraction, we can show that BD is congruent to CD. Now, if you think about it, though, at that point, what would we know? Let's say we'd know this side congruent to that side and that side congruent to itself. So we'd have a side congruent to a side and another side congruent to a side. But that's not enough, right? I mean, in every one of those triangles congruence theorems, even hypotenuse leg, we needed 3 pieces of information, and I'm just going to go out on a limb and say we ain't using hypotenuse leg to prove these two triangles are congruent because they're not right triangles. All right. Ideally, right, I would somehow then prove that an angle was congruent to an angle, or maybe it would be really nice to be able to show this side is congruent to this side. If somehow I could show that AB was congruent to AC, then I'd have these two triangles in red congruent by side, side, side. But the only way I could really show that AB was congruent to AC is if somehow I could show that this smaller triangle here was congruent to this smaller triangle here. And I can do that, right? Because based on the fact that this long side is congruent to this long side, I can then conclude that angle E is congruent to angle F, right? Because those are the base angles of an isosceles triangle. So I'm going to write that down. I'm going to say, show angle B is congruent to angle F. I'm just going to write down base angles here, right? By doing that, right, we can then say that this smaller triangle is congruent to this smaller triangle by side, angle, side. Because of that, I can then show, right, then, let me just write that down. We can show that triangle BEA, actually, let's go with BAE. I can show triangle BAE is congruent to triangle CAF by side, angle, side. That'll then let me get AB. Boy, I'm almost doing the whole proof right here. AB congruent to AC by CPCTC, right? And then that'll let me get these two triangles congruent by side, side, side. We just got to put it all together in an order that makes sense and in a way, right, that kind of logically follows one step after another. All right, so let's do it. Do the formal proof below. Okay, so what I'd like you to do is pause this video. We've done a lot of proof in unit number 3. Pause the video and see if you can work through this proof. Personally, it took me 11 lines to get through the proof. Perhaps you can do it in less, perhaps it'll take more, but go ahead and try to work through it. All right, let's go through this proof. I hope you took some time on that. Now again, remember what we knew. I'm going to kind of mark it on this diagram as well. We knew that this was congruent to this. We knew this was congruent to this. And ultimately speaking, we knew this was congruent to this, although we weren't told that directly. We had to get it from the fact that AD bisected EF. Okay? Again, recall how we're going to do this, right? From our outline, let's go through it. DA bisects EF. Given, right? What do we get from that? We get the fact that EA is congruent to FA. And of course, the reason for that is because a bisector divides a segment into two congruent segments. So far, so good. That's getting us that congruent to that. All right. ED is congruent to FD. Well, that's a given, right? But because of that, I can now say angle E is congruent to angle F. Let me mark those now. Why? Because the base angles of an isosceles triangle are congruent. You could also say angles that are opposite congruent sides in a triangle are congruent, but a lot of people like to say the base angles of an isosceles triangle are congruent. Be careful. Don't say the definition of base angles. That doesn't make a lot of sense. Really get into the essence of it. The base angles of an isosceles triangle are congruent. Okay, but now, because of all of that, right, we can now say, well, we can say that EB is congruent to FC, sorry, and that was, again, just a given. But now we have everything we need to show that those two small triangles are congruent, and in fact, that will be our next step. Triangle EAB is congruent to triangle FAC by the side angle side theorem. That's awesome. We now have this triangle congruent to that one. Why did we do that? We did that so that we could then say that AB was congruent to AC. AB is congruent to AC, and that's by our CPCTC reasoning, right? Congruent parts of congruent triangles are congruent. All right, I'm going to mark that now. 2, 3, 4, 1, 2, 3, 4. Lots of dashes, right? I now know that those two sides are congruent to each other. Okay, now I've got to get that kind of subtraction proof going. AD is congruent to AD. That's just the reflexive property. No problem there. Okay. EB plus BD is FC plus CD. All right, that's just EB plus BD is FC plus CD. Now, keep in mind, right, that step, this step, is really appealing back to the fact that ED and FD are congruent. It is completely okay to restate this in your proof. It's a little bit redundant, but you could certainly do it for clarity. But I'm now really taking that step and I'm breaking those up using the whole as the sum of its parts. All right? Some teachers will just say partitioning there. That's okay. That works. I like the whole as the sum of its parts. Now, why did I do that? Well, I do that, right, so that I can get rid of the EB and the FC. Now again, notice up here, I've already stated that EB and FC are congruent. So I'm going to literally be subtracting this from this to be left with that. Again, can you restate it? Sure you can, but I've done subtraction. Subtraction of what? Line 5 from line 9, right? I've taken line 5, I've subtracted it from line 9, and I've gotten line 10. Now at that point, what we have now is we've got that congruent to that. We've got that congruent to that. We've got that congruent to that. Lots of marks, okay? And we really have everything we now need to make our final conclusion. Triangle BAD is congruent to triangle CAD by the side-side-side theorem. Wow, this is rather long. So I'm going to pause for a minute so that you can write down anything you might need to. Yeah? All right. Let's move on. That will be the longest proof we'll do for some time. All right? It takes a lot of pre-planning, a lot of understanding, right? We've proven a triangle congruent here, another triangle congruent here. Long proof, probably the longest thing that you'd experience on any test. Now let's go with something a little bit shorter. Again, geometry proof and reasoning is always about explaining your thinking, whether it's in a very formal way like in that t-table proof or a less formal way like the problem we're going to do now. All right? Ultimately speaking, it's always about explaining your knowledge and how it connects to other things. So let's take a look at exercise number 2. Explain why the angles opposite the equal sides of an isosceles triangle must be acute. Okay? Well, all right, you have everything you need to do every problem in this particular lesson. There's nothing new that I'm teaching you in this lesson. So take a shot at this. Pause the video now and take a few minutes to think about why this is true, and then try to write something down that you think properly explains it. All right, let's do it. Now, what's interesting about an explanation of this is that almost invariably, or inevitably, you have to do an explanation here that's really what's called a proof by contradiction. Here's what I mean. Let's draw out an isosceles triangle. All right, and let's draw on, the two equal sides, right? And what do we really know? Well, we know that the two angles that are opposite the two equal sides have to be equal. So let's start with that. Actually, let's start with the word the, not the word two. The two angles opposite the equal sides must be equal. Okay, we know that. We don't need to reprove it. We proved it earlier in the angle side lesson. The two angles opposite the equal sides must be equal. Okay. If they weren't acute, well, what would that mean? Right, an acute angle, as we learned earlier this year, and as you've learned in other courses, is any angle that has a measurement that is less than 90 degrees. Okay, less than 90 degrees. So now I speculate what would happen if they weren't acute, right? Now, best case scenario, if they're not acute, then they're both 90, right? Or they're 90, they're above 90. So if they weren't acute, both would be 90 degrees or greater. Okay, why would that be a problem? Well, it would be a problem, of course, because if you add two angles that are 90 or greater to a third angle, which has to be greater than 0, then the sum would have to be larger than 180, right? And that's the end of our reasoning, right? Both would be 90 or greater. When adding the three angle measures together, the sum would be greater than 180 degrees. And why is that a problem? Of course, that's a problem because we know that the sum of the three angles of any triangle must be 180 degrees. And because of that, the two angles have to be acute. So, the two angles must be acute, right? This is a neat way of reasoning. It's called reasoning, indirect reasoning, or proof by contradiction. So we assume the opposite. Oh, why do the angles have to be acute? Well, let me assume that they're not acute, which means that I've got two 90s, or maybe I've got a couple things that are bigger than 90 degrees. And when I add those two angles that are either 90 or larger with this third angle, which again can't be 0, right? Certainly can't be a negative measurement of an angle, not yet at least, right? Then what happens is that my sum by default must be greater than 180 degrees. And of course, if it's greater than 180 degrees, that violates the thing that we proved earlier, which is that the sum of the three angles of any triangle must be exactly equal to 180 degrees. That's it. There's nothing particularly special about this proof other than the fact that you have to work and you have to explain your reasoning in it. All right. So anyway, take a moment, copy down anything you need to, and then we'll move on. Okay, let's do it. All right. So let's go back to a more standard proof, little T-table one here. And again, there's nothing new. Nothing new about any of these things. So what I'd like you to do is I'd like you to pause the video and challenge this proof. Try to work through it all on your own, and then we'll go through all the steps, okay? Okay, let's do it. Exercise number 3, given AF bisects angle BAC and DE is parallel to AB, prove that ADE is isosceles. Okay, so I want to prove that triangle ADE is isosceles, right? Which means I've got to somehow show that it's got two sides that have equal length, okay? I'm not sure which of the sides they are yet, but one thing I'm going to do, because I've got parallelism going on here, and parallelism has to do with a lot with angles, right? Alternate interior angles, corresponding angles, and things like that, is I'm going to label angles all over the place in this diagram, okay? And then hopefully I'm going to move my cursor somewhere else. No, still not. Oh well, my cursor is hanging out on the 1. Not sure exactly how to get rid of it. Hopefully as I write, it'll go away. So I've got those angles numbered 1, 2, and 3, okay? And let me mark up my givens, right? It says given AF bisects angle BAC. Well, what will that tell me? It'll tell me that angle 1 and angle 2 are congruent, okay? And DE is parallel to AB. DE is parallel to AB. What two angles do you know are congruent based on that? Do you know? Well, I can actually say that angle 1 is congruent with angle 3 based on that. Okay? You probably already have a sense for how this proof is going to play out. Think about this. I know angle 1 is congruent to angle 2 because of the angle bisector. I know angle 1 is congruent to angle 3 because of the parallel lines. So by substitution, I can then say that angle 2 is congruent to angle 3. But then I have two congruent angles in a triangle, which means the sides opposite of them must also be congruent, which means I've got a triangle with two congruent sides, and therefore it's isosceles. Let's take a look at how this all works out. All right, AF bisects angle BAC. Simple enough, given. Angle 1 is congruent to angle 2. Also easy enough. Well, an angle bisector divides an angle into two congruent angles. Simple. DE is parallel to AB. Again, it's just a given. Angle 1 is congruent to angle 3. The wordiest reason now, alternate interior angles created by a parallel line cut by a transversal are congruent. I think best case scenario there is you could cut that down, if you didn't want to do all that writing, to say alternate interior angles created by parallel lines are congruent. You could probably get rid of the cut by a transversal piece, but you got to have the parallel lines in there. You have to have the alternate interior angles. Try not to call them alternative interior angles. That makes it sound like they're in some kind of punk rock band. You know, alternate interior angles. So, right, 1's congruent to 2. 1's congruent to 3, therefore 2 is congruent to 3. That's substitution. Again, your teacher might call it the transitive property of congruence. That's okay as well. I like to think about it as substitution. I'm just substituting 2 for 1 in this equation. That kind of sounded funny. All right, but now, and this is a really key piece of reasoning, anytime you have a triangle that has two congruent angles, like 2 and 3, the sides that are opposite of those angles are also congruent. Okay? So I can now say that AD is congruent to ED because sides in a triangle opposite congruent angles are congruent. Be careful, don't say something like the definition of an isosceles triangle or anything like that, right? The plain fact is, I'm trying to prove this thing is isosceles. I can't use the fact that it's isosceles to prove it. That doesn't make any sense. Okay? Finally, I can say the triangle ADE is isosceles, and now it's completely okay to say the definition of an isosceles triangle. Or you could say something like, because triangle ADE has two congruent sides, it must be isosceles. All right, let me pause a little bit so you can write down any of these statements and reasons that you need to, and then we'll move on to do another proof. Yay, more proof. All right, let's do it. Ooh, okay. Now, not the next unit. The next unit's all about constructions. We're going to do a lot of drawing and manipulating and things like that. And not the unit after that. But after that, we're going to get into all sorts of things like parallelograms and rectangles and squares and shapes like that. So here, we're going to kind of look at a proof that we'll see a little bit later on, but that we have all the tools we need right now. All right. It says, given that QP is congruent to RS, and that QR is congruent to PS, nothing wrong with like marking those down, prove that QP is parallel to RS and QR is parallel to PS. Sorry, I read those a little bit out of order. Now it says, hint, draw in QS. One of the tricky things about geometry is that you can always draw in extra line segments. You know, there's between any 2 points, like Q and S, right, there is a line segment, right, QS. And we can draw that in if it helps us. The reason, of course, it would help us to draw this thing in, hopefully draw this thing in, is that it creates 2 triangles. And by the looks of it, it creates 2 congruent triangles. Now remember, parallelism, and specifically proving that things are parallel, is all done by proving that angle pairs, special angle pairs like alternate interior angle pairs and corresponding angle pairs, are themselves congruent. So I'm going to throw in a bunch of angles as well. All right? I'm going to label all those angles. All right? I could also label angle P and angle R, but I don't really need to, right? I could just call them P and R if I had to. Okay. Now think about this for a second. Right now, of the 2 triangles shown, I have a side equal to a side equal to a side, and then they have a shared side. side QS. In fact, I think I'm going to mark that right now. Right, a shared side QS. So right away, I have a sense for how this proof is going to play out, right? I know that those two triangles can be proved congruent by side, side, side. Because they're congruent, and this is a little bit difficult to picture, I'll then be able to say angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. I'll be able to say that using, oh, that's right, CPCTC, right? My favorite line of reasoning. But if you notice, right, angle 3 and angle 4 are alternate interior angle pairs, and so are 1 and 2. And so once I know that alternate interior angle pairs are congruent, I can say that lines are parallel. And I essentially have the whole proof. In fact, take a little bit of time and see if you can write the proof down. Okay, let's go through it. I mean, we've kind of scoped the whole thing out. Here we go. QP is congruent to RS, and QR is congruent to PS, side and side. And those are just givens. All right. Then I can say that QS is congruent to QS. That would be the hardest part of this proof if that hint wasn't drawn, or that hint wasn't given, right? Because I don't see QS up on the original picture, but it can always be drawn. And that's the reflexive property. We know that. Anytime you state that something is congruent to itself. Then we've got triangle PQR is congruent to triangle RSQ. Sorry. And that's simple by the side, side, side theorem. Based on that, I can now say angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 by CPCTC. Okay? Let me mark those really quick. Angle 3 is congruent to angle 4. 1 is congruent to 2. I hope, based a lot on our work in rigid body motions, that you can see that, right? That in fact, this triangle and this triangle are congruent, but it would really be taking this one and kind of rotating it by 180 degrees, and we would see then the angles that are congruent to each other. So finally, I can say that QR is parallel to PS, and QP is parallel to RS, because if a pair of alternate interior angles created by, it should be created, not creates, created by two lines cut by a transversal are equal, then the lines are parallel. Again, the angles of the Z. If I've got this kind of scenario, and I know these two angles are congruent, then I know these two lines are parallel. Okay, and we saw that a few lessons ago when we did sort of our work with more parallel line properties, which could have also been entitled, How do we prove lines are parallel? Okay, it's kind of a neat proof. Again, let me step out of the way so that you have a little bit of time, and then we'll move on. All right, let's go through one more. Exercise number 5. All right. Explain why, when two parallel lines are cut by a transversal, as shown below, the two interior angles on the same side of the transversal, 1 and 2, must be supplementary. All right. Now again, this is going to become important because eventually when we work with parallelograms and rectangles and things like that, we're going to want to be able to conclude very quickly that two angles, like 1 and 2, that lie on the inside of parallel lines and on the same side, so they're literally called same side interior angles, you know, we want to be able to look at that and go, oh yeah, they're supplementary. Okay? Take a little bit of time and see if you can make an argument for why they're supplementary. All right, little paragraph proof to end the lesson. It's this simple. Okay. Angle 3 and angle 2 are supplementary because they form a straight angle. right? These two are supplementary because they form a straight angle. On the other hand, angle 1 and angle 3 are congruent because they are alternate interior angles created by parallel lines. All right. That means by substitution, right? What do I mean by substitution? It means I can literally substitute angle 1 for angle 3. That means by substitution, angle 1 and angle 2 must be supplementary. All right? And it's kind of cool, right? You could definitely make the argument in different ways. All right, but you should almost be able to picture it. In fact, if I change the pen to red, really quick, maybe make my line thickness a little bit bigger. If I actually outline angle 1 like this, and then I move it up, right? And we kind of knew, of course, that angle 1 and this angle should be congruent because they're corresponding angles. But what we see is that when we combine angle 1 with angle 2, they form a straight angle, right? And that's kind of the idea of supplements. When you put two angles together so that they share a common ray, if their other two rays then form a straight line or a straight angle, right, then they're supplementary. That's kind of neat, right? Just a translation. And you could make that argument that way. You know, we could have another angle up here, angle 4, and we could say angle 2 and angle 4 are supplementary because they make a straight angle, and angle 1 and angle 4 are congruent because they're corresponding angles, etc., etc. All right, but we did it the way we did it. So let me pause for a second, let you take a little bit of time, and then we'll wrap up the lesson. All right, let's do it. So there was nothing new in today's lesson. What I wanted to do was give you some more practice with the major triangle theorems, all right, how to apply them. I wanted you to see a longer proof like exercise 1, and then some shorter exercises where you had to explain again your geometric reasoning and your geometric knowledge, okay? But that really wraps up Unit 3. It really wraps up our look at how triangles can be proven congruent and then what you can do with congruent triangles. Now, it's not the last time we will see this, especially when we get into unit number, I think it's 6, okay, on quadrilaterals, and we investigate parallelograms and rectangles and squares. Almost always what we're going to be doing is taking those four-sided figures and breaking them into two triangles, and our ability to prove that those two triangles then are congruent are going to allow us to prove many interesting properties about the special quadrilaterals. But that's still a couple units from now. We've got a whole lot of constructions and some coordinate geometry between now and then. So for now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.